Newton's cradle is a really fun little toy. I'm sure a lot of you have seen it. If you look at the image on the left-hand side here, you can see that when a single ball, and all of these balls have got the same mass incidentally, when a single ball is pulled away and released, it'll gain kinetic energy from the gravitational potential energy that it had through mgh, and as it swings towards the rest of the balls, at the point of impact it will have velocity v, and we can see that momentum transfers between the balls and out the other side with velocity v comes one of the other balls. The interesting thing is, when you take two of the balls to the top, so you have 2m, as they come in and impact the 3, they have again velocity v, but this time 2 of them, but now 2 will come out the other side. So we have 2m with the same v over here. Or another way of thinking about it is, the momentum that was put in is the same as the momentum that comes out. And that's the principle of conservation of momentum. In a collision, momentum is conserved. The momentum after the collision is the same as the momentum before, assuming that there are no external forces acting on the system. This is a definition you need to learn. And this is the formula version. If I have two objects, m1 coming towards m2, or m2 could also be moving towards m1, or m2 could initially be moving slightly in that direction, the initial momentum of m1 plus the initial momentum of m2 has to equal the final momentum of m1 plus the final momentum of m2. And in this scenario, thinking about your directionality is especially important. Let's look at a couple of simulations then. Here I've got mass m1 and mass m2. Now we're told, if you look at the bottom here, that 1 has a mass of 0.5 kilograms, m2 has a mass of 1 kilogram, and m1's initial velocity in this direction is 3 meters per second, m2's velocity is 0. It's at rest. Let's have a look at what happens as they collide. M1 toddles off. As they collide, they move apart. M1's now changed its direction, so it's now moving in the negative direction. M2 is moving in the positive direction. M1 is moving in that direction with minus 1 meter per second squared. M2 is moving in this direction with plus 2 meters per second squared. And we know from conservation of momentum that if this is allowed to take place, m1u1 plus m2u2 has to equal m1v1 plus m2v2. Is that the case? Well, m1u1 is 0.5 times 3, which equals 1.5 kilogram meters per second. m2u2 is 0, so total is 1.5 kilogram meters per second. On this side, m1v1 is 0.5 times minus 1, which is minus 0.5. m2v2 is 1 times plus 2, which equals 2. So we have a total of 2 minus 0.5, which equals 1.5 kilogram meters per second. It works because of conservation of momentum. And this works if they approach each other as well. They've got the same masses, but this time m1 is moving with a positive velocity of +2, m2 is moving with a negative velocity of -1, and they're moving towards each other. As they impact, they're going to rebound and switch velocities. And their final velocities, m1 is moving at -2 in this direction, m2 is moving with +2. So m1u1 plus m2u2 equals m1v1 plus m2v2. Let's see what we get here. Well, m1u1 was +2, velocity times the mass of 0.5, which equals 1. m2u2 was 1 times -1, which equals -1. Therefore, total momentum here was 1 minus 1, which equals 0 kilogram meters per second. But on this side, after the collision, my 0.5 kilogram mass is moving with -2, which gives me a total of -1 kilogram meters per second. My larger mass was moving with a velocity of, oh sorry, that should have been +1 there. That gives me a velocity of +1. So my overall momentum is -1 plus 1, which equals 0. Momentum before is the same as momentum after. So let's look at the kind of question that you might get on this. An alien with mass of 4,500 kilograms running along at a speed of 3 meters per second, so there's m1, u1, collides with a stationary alien, so we know that u2 is 0, and that has a mass of 3,000, and they stick together as they collide. Calculate the speed of the aliens immediately after the collision. Well, I have my mass of 4,500 moving in this direction towards a stationary 3,000, and it's always good to draw your scenarios out. This is before, and we're going to want to do after as well. m1u1 plus m2u2 equals m1v1 plus m2v2. So on this side, 4,500 times the velocity of 3 meters per second gives me a momentum here of 13,500 kilogram meters per second. This one here has a velocity of 0, so we don't have any momentum for that. After, they both stick together, so I have a total mass of 4,500 kilograms plus 3,000. And we want to work out what the final velocity is. So I know that my momentum afterwards has to equal the momentum before. So it has to equal 13,500 kilogram meters per second. Now I can, because they've stuck together, model this as one giant particle. So I can say that the momentum before has to equal mv, where m is 4,500 plus 3,000, times the velocity that I'm looking for. That means that my v is simply going to be 13,500 divided by 4,500 plus 3,000. And when I plug those numbers in, I get a final velocity of 1.8 meters per second.